Hello, I'm David. It's summer semester 2019, and we have a revision seminar for Maths 1B, which has got requests. People have written some things on the blackboard that I may or may not cover, and so far I've chosen that I will talk about the multivariable calculus critical points and orthogonal projection first, and then I'll see where I get to after that. So that's what we're going to do. If you think of anything between when I stop one thing and when I start the next, feel free to tell me and we all come and write it on the board. But I do not promise to cover everything because, you know, if there are enough people in the room, you can usually get the whole course on the blackboard there, and that takes a lot more than 2 hours. So we'll see what we can do. But first I'll start with critical points and maximums and minimums for multivariable calculus. Okay, so the general idea is that you've got a function and it takes, usually in this case, 2 variables and produces a single output number. Something like that, a function that takes R2 in and spits R out. So for example, you might take the point x, y, and it might produce, x squared y minus y cubed plus x, or something like that. And what this does is for every point x, y, you use those coordinates and it produces a number. And every coordinate produces a number, and what we're interested in is where is the maximum number that it produces. So that's what we're interested in. Where is the maximum and minimum? And various just other things about shapes. So it's a similar problem to ordinary calculus, one-dimensional calculus, where we had a number. My actual microphone wasn't even on. Oh well. Where we have a number that gets spit out, and we just have an x instead of both an x and a y, and we try and figure out which x's make the output the biggest or smallest. And one of the ways of dealing with that is just to find the local maximums and minimums, which are the places where it's bigger or smaller than the ones nearby. I shouldn't use larger. Greater or less than the outputs nearby. Okay, so that's what we're going to be looking for, local maximums and minimums where the output is greater than or less than the outputs nearby. Okay, so if you interpret your function as a height or a depth, you've got an x and a y coordinate and you have a height or a depth, then here it is. Then you might be able to have an xy coordinate down below somewhere, and then your function values are heights, and it will produce some sort of a surfacey thing. And this surface has been specially designed in my sandpit and with paper mache to have various things. So this point here is higher than all of the points everywhere. This is the global maximum just here. And this point here is higher than the points nearby, but it's not the actual highest point. This is a local maximum. It's higher than the points nearby. This point here, in this valley just here, is lower than every... No, it's not. This point here is lower than the points around it. It's in the bottom of a valley. It's a local minimum. This is a local minimum as well. It's lower than the points around it. But if I turn it this way, you can see that this one's actually lower than everything around it. It's the global minimum. Okay, that's what we're looking for, these humps and valleys when we're doing our maximums and minimums. And there are some other points that are rather interesting, which is this one. This one just here is the bottom of this valley, but it's the top of this hill. So if in some directions it's a maximum and some directions it's a minimum. It's not really a maximum or a minimum because there are some points above it and some points below it, but something interesting is going on there. That's called a saddle point. Because, well, if these were the humps on a camel and you put a saddle on it, that's where you would be sitting. That's why it's called a saddle point. So they're the points we're going to be interested in, and they will be related to how the derivatives behave. Okay, so let me do some more maths and I'll come back to our picture in a second. But I will attempt to draw something as well. That's an awful picture. Thank you for bearing with me. So this would be a local maximum. This is a local maximum. This is a local minimum. And then here in the middle we've got a saddle point. See the video, but I just wanted a quick picture of what was happening in the video, so that if all you had was the written version on the the PDF, then you could have something. So that's what we're interested in, and what we're going to do is we're going to use derivatives to find those. So in the seminar on Friday, I said, and I'm going to repeat it now, the thing that we're really most interested in before we get to this stage is the directional derivative. We know that if we have a point xy on the xy plane, we can move in multiple different directions, and we can be interested in whether it's going up or down if we move in those directions. So what we would like, a local maximum is a point where if I'm standing on it and looking from above, no matter which way I go, the surface goes down from there. So I'm going to just get my camera back again. If I'm standing here, no matter which way I go, that way or that way or that way or that way, if I go any distance that direction, the surface goes down from there. But at this exact point, if I'm coming past this point, travelling this way, travel this way, the surface goes up and then it goes down. If I'm travelling this way, the surface goes up and then it goes down. If I'm travelling this way, the surface goes up and then it goes down. No matter which direction I approach this point from, the surface goes up and then down. So at this exact point, in every direction, the slope is 0 at this spot, no matter which direction I come from. So at a local maximum, that will happen. No matter which direction I approach this spot from below, I'm approaching on the x and y axes, no matter which direction I approach that from, the slope is 0 at this spot. And that happens at the bottom of the valley as well, down here. And it also happens just here too. No matter which way I go from this point towards this point, it will be either a maximum or a minimum. But sometimes there's one and sometimes the other. So at all of these 5 points, no matter which direction I approach them from, the slope is 0. So at a local maximum min or a saddle point, the slope is 0 from every direction. Of course, if it comes to a sharp point, then there's no slope there at all, so that would be a place where the derivative isn't defined, but we haven't really talked about that in multivariable calculus, but it is technically possible. So at a local maximum, minimum, or a saddle point, the slope is 0 from every direction. And the way that you calculate a directional derivative is to do the dot product of the gradient with the direction that you're moving. So if you want, the directional derivative of u at this point AB of f is 0 for all directions u. But the thing is, this is the gradient of f at AB dot with u. And the only way you're going to dot, and this is a vector here that has the two partial derivatives in it. So the only way you are going to arrange for this vector dot u to be 0 no matter what u is for this vector to be 0, the 0 vector. And so therefore we're going to have, so I need the gradient of f at AB to be 0, which means that the two partial derivatives in the x and the y direction both have to be 0. And if they're both 0 in those two directions, then it will actually, the gradient will be 0 in every direction, which is nice. In fact, that would probably happen if you had two different directional derivatives coming out to 0 in two different directions, and all of them in every direction is 0. So that's what we need to get a local maximum or minimum. The next stage is to figure out whether it's a local maximum or a minimum or a saddle point or something else stupid is going on. But it has to be one of those situations. It can't be anything else. So we can do a second derivative, which I'm not going to explain how that works because it's a bit mysterious to me. But we can do a second derivative to tell which of those kinds of things that it is. So this is our process. I'll just write that down. To tell if it's a maximum or a minimum or a saddle. Well, I know, one thing that I do know, that the second derivative, if I'm moving in the x direction and this is the top of a hill, then it's concave down at this point from the x direction. So if it's concave down in the x direction and concave down in the y direction, it's probably a local maximum. So if this is the y-axis here and it's down here and down here, probably a local maximum. And if it's concave up in both directions, it's probably a local minimum. And if it's concave up in one direction and concave down in the other, then that would be a saddle point. So it would be useful to have a second derivative in those directions. But the problem is you can have some wickedly strange saddle points that are concave up in both of these directions, but then have it goes sort of up and down multiple times. This one only goes up and down 4 times, goes up, down, up. But you can have ones that go up, down, up, down, up, down, up, down as you go around. And so you can accidentally get the concave up in both the x and the y direction and it still be a saddle point. So we have to somehow include some other information to get the thing that we want. And the way that we do it is that we calculate all of these things. Calculate this D, which is the determinant of this matrix at the point AB. And then if this comes out as positive, then it's concave up. And if it comes out as negative, it's concave down. And if it comes out as positive, then it's either concave up or concave down, one of those. And if it comes out as negative, it's a saddle point. And if it comes out as 0, well, we don't know. So then we get this. I'm just going to summarize all this again in just a second. So D is positive, then it's max or min, but it doesn't tell us, the D itself doesn't tell us whether it's a maximum or a minimum. And D is negative, it's a saddle point. And if D is 0, it tells us nothing. And the problem is that this D being positive doesn't tell you whether it's a maximum or minimum, it just tells you it's one of those two. And the only way to tell is to look closer. Well, you know if it is either a maximum or a minimum, and it's concave up based on this information here, then it must be a minimum. And if you know it's a maximum or minimum, and it's concave down based on one of this information here, then it must be a local maximum. So I'm just going to change that here. So this one, if fxx or f of x, fyy is positive, then it will be a minimum. And if fxx or fyy is negative, it'll be a maximum. And d equals 0, we don't know. So I'm going to rewrite that as a table in a second. So to me, the bit of this that makes the most sense is this bit. fxx is the second derivative when I'm looking in the x direction. And if that's positive, it's concave up when I'm just going in the x direction, which means it must be a minimum in that direction. Before you even calculate the rest of this, if you know that this is positive, then you know it's a minimum in at least one direction. And so if it's going to be anything, it's either going to be a saddle point or a minimum. And if it's negative, the other way around. So I'll get to using that in just a moment. Okay, so let me just sum that up. Okay. So to find local max, local min, or saddle points, find f of x and f of y. Find all combinations x, y where both f of x equals 0 and f of y equals 0. You need them both to be 0 at the same time for it to be a local maximum or minimum or saddle point. And 3, find d at those points, and then we'll get exactly the thing that I said before. D is positive, means local max or local min. Yeah, that's not how you spell local, David. Where'd my eraser go? And you've got two options. Then it means it's a minimum. So that positive is because it's concave up, which means minimum, or that means it's concave down, and so it's a maximum. Now the other thing that might happen is that D could be negative, which makes it a saddle point. Or it could be that D is 0, which tells us nothing, which means we might have a hope if we go back to here and find that one of them's positive and one of them's negative. Actually, no, that'll always be a saddle point. So, yeah, we would have come out as this being negative if we did that. So if it comes out to be exactly 0, well, you haven't been taught ways of dealing with that. My way of dealing with that would be to look at the directional derivative at all of the points nearby and see what we get. Or just look at the function values at at several points nearby and see if some of them are above and some of them are below. Yeah. But basically, I'm pretty sure that the lecturer just hasn't taught you what to do here, and so you just say, test fails, sorry, dude. Okay. That's the plan. So we should do it. Oh, give me a second. Yeah, go for it. Like that. You could imagine actually, doing this bit first and going, well, if one of those is positive, then you know it's either a local minimum or a saddle point, and then deciding afterwards, after you've done the actual derivative, the actual discriminant. Okay, so I need a function just a second. Can't remember how I make that function. I'm just going to do it and see what happens. This could turn to crap. Yep.
So on that previous page there, you said if fxx or fyy is positive, then it's concave up. Like you have that part there. What if they have opposite signs?
Then it's definitely a saddle point. So if you have fxx being positive and fyy being negative, that's what you're talking about?
Yeah.
So that means that if I'm looking in the x direction, it's concave up, and if I'm looking in the y direction, it's concave down, which means that it has to be a saddle point.
Okay.
So when I say concave up, I mean it's concave up in that direction. Yeah. Okay. Does that help?
Yes.
Okay, good. So yeah, if one of them's positive and one of them's negative, it's guaranteed to be a saddle point no matter what. Okay, let's try this one. So here's a function. Oh, just a second. There you go. Stick a minus there. That's important. Okay, so it's x plus 1 times y minus 2 times e to the minus x squared plus y squared. And let's see if we can find the maximums and minimums of this point, this function, or saddle points if it's got any, and see what we get. So, derivative with respect to x. So in that case, this counts as a constant, and I have two pieces multiplied together here that both involve an x, so I'm going to have to use the product rule. Okay. So let's see. The derivative of this bit is, well, the y minus 2 is a constant, so it will still be there, and the derivative that's multiplied on, so it'll still be there, and the derivative of x plus 1 is 1, and then I'll keep this bit. And then we'll keep this bit. And the derivative of this would be the same, because that's how e works, but we'll have to, because of the chain rule, multiply by minus the derivative of this with respect to x, which is 2x, because the bit involving a y wouldn't do anything. Sweet. Okay. I feel like I ought to factorize this a little bit. Both of them have a y minus 2 and an e to the minus x squared plus y squared, so I might pull that out. And then what are we left with? A 1 and an x plus 1 times minus 2x. Okay. Yep. So 1 minus 2x squared minus 2x. I think that's right. Yep. Okay. That's the x derivative. And the y derivative, let's see, still going to have to use the product rule. That's a constant multiplied on the x plus 1, and the derivative of y is 1. Keep this bit. And then we'll keep the x plus 1, y minus 2, and then we'll have we'll have to times by the derivative of this, which is minus 2y. Okay. So let's go to x plus 1. Oh, that's rather interesting. Oh, that'll be a plus. That was an x plus 1. That's okay. Everything's good. Right. So, if I want to find the local maximums and minimums, I need both of these to be 0 at the same time. So I need them both to be 0 at the same time, which means, usually the easiest way to deal with that is to make one of them 0 and figure out the x's and y's that do that, and then sub those into the other one to make sure to figure out which of them make the other one 0 at the same time. So I may not get any, and then the whole thing turns to crap, and I'm sorry in advance, but at least you saw some good partial derivative work. So let's see, if f of x equals 0, that means that I've got 1 minus 2x squared minus 2x times y minus 2 times e to the minus x squared plus y squared has to be 0. Okay, and this is never 0. And we either get 1 minus 2x squared minus 2x is 0, or y minus 2 is 0. Because it's two things multiplied together to give 0, one of them has to be 0. I've just minused everything and put it in a standard order. I don't feel like attempting to factorize that, so I'm going to use the quadratic formula. Minus b plus or minus the square root of b squared minus 4 times a times b over 2a. Oh, sorry, I just did all of that work saying it aloud. Minus b plus or minus b squared minus 4 times a times c divided by 2a. So what have we got? 4 plus 8, which is 12. I don't like it. It's awful. It's bad. I guess 12 is 4 times 3, so I could square root the 4 and that'll give me 2 root 3. It's not good. Interestingly though, like a half and root 3 on 2 are a sine and cos of like pi on 6 or pi on 3, depending on which one is the correct one. Okay, so I have three possibilities. I have that x is this, x is one of these two numbers and y is one of these two numbers. This is telling me that if x is one of these two numbers, then regardless of what y is, f of x comes out to be 0. And if y is 2, then regardless of what x is, f sub x comes out to be 0. That's what this tells me, because it's this or this. Okay, so what I'll do is I'll sub those three possibilities into the other one and see what happens. And see if any of them come out to be 0. So f of y was, f sub y was okay. So if x was equal to minus 1 plus or minus root 3 over 2, well, oh wow. I've made myself pain here. Actually, it's regardless of what x is here, just here, I need this to be 0, right? I want that to be 0. So if x is this, then it doesn't... Okay, so maybe subbing it in isn't the best plan. I'm not going to do that. Sorry. Subbing in is sometimes a good plan. Today, not so much. Let's just solve the other one. Okay. So let's also solve f of y equals 0. And so we're going to get this equals 0. That's not 0, so we get x equals negative 1 from here. And 2y squared minus 4y minus 1 equals 0 from here, which means y equals minus b plus or minus b squared minus 4 times a times c over 2a. 16 minus... Oh! Sorry? Oh yeah, plus. Well done. You're right. It should totally be 24. Thank you. So 2 root 6. Not very nice. So this is telling me, what have I got so far? So far, I have that if x is this or y is this, then fx comes out to be 0. And if x is this or y is this, then f of y comes out to be 0. So what we need to do is choose combinations of x and y where both of them come out to 0. So I could choose minus 1 plus root 3 over 2 to make the fx 0. And y equals 1 minus root 6 on 2, which makes the fy equal 0. Or this makes the fx equal to 0 and this makes the fy equal 0. Okay. Or I could choose the other option for this. Okay, so this makes the fx equal 0, this makes the fy equal 0. Or I could choose y to be 2, which makes the fx equal to 0, and pick an x that makes the y equal 0, which would be x equals minus 1. So what I've done too is I've run through all of the ways to make fx equal to 0, here, 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 like here, here, and here. And then chosen something that makes fy equals 0 at the same time. So what I've ended up with is 1, 2, 3, 4, 5 critical points. Hooah! Okay. Am I going to commit to the algebra to figure out the second derivatives from this information or not? Do you want me to or not? Because I don't fancy finding those second derivatives.
What would be most beneficial for us?
That's a good question. I think I would prefer to move on and do another example where the algebra is a little easier so that I can get to that second bit faster. And that has a different way of finding the multiple critical points than what I did just then. Okay, thank you. So one of the things what happened in this one is I found all of the combinations, all of the x's or y's that made fx 0, and all of the x's or y's that made fy 0, and then I matched them up with each other to find all the combinations that made them both 0. That's what I did here. So my critical points actually come out to be these 5 points. Incidentally, that's the sort of thing that produces this graph here. This graph is something like the one that I drew there. And it has 5 critical points. 2 of them are maximums, 2 of them are minimums, and 1 of them is a saddle point. And that would produce that answer there. Okay. I wish I had an example pre-worked out, which I really should have done, knowing I was going to do this, that will work out to be the thing I want, that will work out the way I want, but I don't, so I'm just going to try and use the one that I started with. That one, and see what happens with this. So f sub x, so the y counts as a constant, so it will still be there, constant multiplied on, so it will still be there, so we'll have a 2x. This y is a constant added on, so it won't do anything, and we get a plus 1. And if y, x squared counts as a constant multiplied, so it's still there, y, that'll be a 1, that'll be 3y squared, and x disappears. Okay. So I need to find the combinations of x and y that make both of these 0 at the same time. I don't even know if there are any. Okay. So I need 2 times 2xy to plus 1 to be 0, which means that 2xy is minus 1, which isn't the best. All right. I guess xy is minus a half. Can I get y equals 1 over 2, minus 1 over 2x? That's a thing that could happen. Okay. All right, let's try the other one. So I need x squared minus 3y squared to be 0. So x squared is 3y squared. X could be plus or minus root 3y, I suppose. I need the plus or minus because the square root, I could put positive or negative x's in there, so that would be okay. Okay. So looking at both of these, I've gone as far as I think is reasonable. I could sub this one into that one and see what I get. Or maybe multiply this one by y, because I know what x times y is. But technically there's 2 equations here, and it might be easier to actually treat them separately. So what if I sub this one into that one? And so I'll give them numbers. This is 1, this is 2, this is 3. Sub 1 into 2, in which case I'm going to get root 3y times y is minus a half. So y squared is minus 1 on 2 root 3, which has no solutions. Okay? Because, you know, there would be imaginary numbers there. Can't get a square to be negative. Well, that's 3, sorry. So the second one into 3, so we've got minus root 3y times y. It's minus a half, so I sub this one into there. And so I get y squared equals 1 on 2 root 3. Oh, wow. So y is equal to plus or minus 1 on the 4th root, the square root of that. Ah. Sweet. 2 root 3 is root 12. All right. There it is. That's the answer. And so since I have some answers for y, I can figure out what the x has to be. So I have that, and so we have y equals 1 on the 4th root of 12, or y equals 1 on the 4th, minus 1 on the 4th root of 12. And so therefore x, which was equal to minus root 3y, because that's the formula we use to get this, we use number 2, which is that one there. And so that would be minus root 3 on the 4th root of 12. and x is root 3. Okay. So at this stage, it's really important to keep track of which x goes with which y. This y is one of the options, and this x goes with it. And this y is one of the options, and this x goes with it. So in this one, what I had to do is I had to sub one of the equations into the other one in order to get a solution, something that was in terms of only x or y. And once I found them, I could sub those answers back into either of those equations. Okay. Right. So I've got these two critical points. One on that one and this one. Oh, like that. Cool. So I would like to know whether those critical points are saddle points or whatever they are, and so I'm going to have to do my second derivatives now in order to do that. So we're going to need to classify them, which means I'm going to need to know all of these things. So let's see. fx was 2xy plus 1. So if xx, okay, so the 2 and the y count as constants, and the derivative of x is 1, and that constant disappears. Okay, fxy. Now we differentiate this with respect to y, we'll just get a 2x. fyx, well, that'll be the same because it's a nice function, but let's just check if we've done it right. fyx, differentiate this with respect to x, we'll get 2x, and that'll disappear. Yep, that works. And fyy, that disappears because it doesn't have any y's in it, and we get minus 6y. So these are our 4 second derivatives, and so my discriminant at xy is the determinant of this matrix. So I get minus 12y squared and minus 4x squared. I don't even need to sub anything in. That's always negative no matter what x and y are. So I don't have to do anything for that one. That was lucky. They're both saddle points. But just for completeness' sake, when I sub in this point into this discriminant, I get minus 12y squared and minus 4x squared, which is negative, and so it's a saddle point. Because I got minus something, minus another thing. And d of so this function doesn't have any local maximums or minimums, it just has 2 saddle points. No idea what that looks like.
How would you not have a local max? Because it's got to go up to somewhere and then down.
Well, I know it doesn't have a global maximum because if y is 0, x can be as big as I want. So it definitely doesn't have a maximum. It can go up as far as I like. So I know that my instinct tells me that it should definitely not have a proper maximum. But why wouldn't it have any local maximums? I think it's probably, if I picked a specific, let's just think about that. If I pick a specific y, then it's like a quadratic, like something x squared plus x minus something. And that quadratic will, and it's if the y was positive, that quadratic totally would be facing upwards, and I'd get a local minimum in that direction. But as the y moved, that local minimum would become a local maximum somewhere. as the y changed from positive to negative. So if that y was positive, I get a local minimum. If that in the x direction, if that y was negative, I get a local maximum in the x direction. And the place where it switches over is probably that saddle point. Could be wrong about that. But I have a feeling that if I had any particular point, so let's just pick 1, 1. At the point 1, 1, I've got x squared plus x minus 1, which is an upwards facing parabola, so it's a local minimum when I'm thinking about x. And if I pick x to be 1, I get y squared minus y cubed plus 1, which is a cubic. And I have no idea what that cubic is doing at that point. It could be going up or down. So it might be a saddle-y thing going on there. So yeah, this is a really weird-ass function. So in some directions it's facing upwards, in some directions it's facing downwards. But only some of those places is the derivative equal to 0. Okay, so in this one, the place where the x derivative is 0 is not the same place where the y derivative is 0. And so it doesn't turn out to be a critical point. That happens on this curve too. And this function, this surface as well. At say this point just here, if I'm looking in the x direction, maybe it's facing this way. If I'm looking in the x direction, it's a maximum. But if I'm looking in the y direction, it's nothing. It's just somewhere in the middle of the curve. It's not a maximum or a minimum. And that'll happen all over the place. There'll be some points that are a maximum in one direction and nothing in the other direction. Only the places that are a maximum in both directions can be local maximums. And so what we have for this function is that the two critical points we found are both saddle points, and I have no idea how that's even possible. Yep. Actually, when x is 0, we get minus y cubed, so it's got this like inflection point there when x is 0 for every possible y. So that's yeah, anyway, I've really got no idea what's happening in this function, but I do know that it doesn't have any local maximums or minimums. Puzzling, but totally possible. It's at least good to know that that's possible. Right. Damn it, I keep forgetting to switch cameras. You'd think I'd be good at it after 3 revision seminars, but it just gets worse as I go along. So any other thoughts about this maximums and minimums of multivariable functions or questions you want to ask before I move on? And I don't have to move on. I'm happy to talk about this for a while longer. Or a specific example that you've seen that stressed you out.
So if we get like the test is equal to 0,
Yep.
is it just acceptable just to say? Or
Yeah.
there's something more,
I think it's okay. Suppose, f of x, y equals blah, 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 and then you find fx equals 0, fy equals 0, blah, 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 something like that. And then you get the d, and it comes out to 0. That's just the general idea you're talking about. And you're going, well, what do I say? I think it's okay to say the test fails. It's a critical point, but I don't know whether it's a maximum, minimum, or a saddle point, and just say that. So 1, 2 is I cannot tell if it is max or min or saddle point. And just leave it at that. I think that's okay. Because as far as I can tell, looking at your notes that were given out for Maths 1B, it doesn't give a way of resolving that issue. Yeah. The only thing I can think of is in the exam, they may get you to note that in an exam it may come out that it comes out as 0, and then they'll give you some extra things to do that you might not have seen before that might allow you to decide that it's a saddle point. So what they might get you to do is calculate the actual function value at several nearby points and go, well, it can't be a maximum or a local maximum or minimum because this one's above and this one's below. That's the only thing I can think of, but I don't think they expect you to do that unless they ask you to. Yeah. I always like to imagine how they could get around it without teaching you something new, but I can't think of many ways. Yeah. Okay. Next thing on my list was orthogonal projection and, importantly, the matrix therefore. Okay, so we're squarely in algebra territory now, though still thinking functions actually. So an orthogonal projection is a kind of function. It takes vectors often in 3D and produces new vectors as the answer. And the way that it does this is it finds the nearest vector on a subspace to the vector that you first thought of. I might need someone's notes to look up what the notation for it is this year. We never used to have a notation for this, and now we do. Okay. So here's how we set it up. So we pick a subspace called V, and then we pick a point called, say, U or X or W, doesn't really matter. I'll call it W. Then the orthogonal projection of W onto V, that's how you say it aloud, orthogonal projection of W onto V, whose notation is the projection onto V of W. So that makes it sound like, what's the point of saying orthogonal if, why isn't it OP for orthogonal projection? Just note that in this course and in pretty much all maths courses, when they say projection, they always mean orthogonal projection. So is notated like this, the projection onto V of W, and this is the nearest point to W that's in V. That's not a definition, but that's the basic idea. So just as an example, it's going to be completely a pictorial example. Here is a subspace in R2, that's my V. And here is a point W, which is somewhere, and I want to find the nearest point on this line to this point here. So I will come along and I'll go that one. That's the projection onto V of W. And the reason why it's called an orthogonal projection is that once you've found it, you are guaranteed that this angle here is a right angle. Because moving at right angles is the best way to go the shortest distance. Okay, so that's not the definition. I believe the definition is the unique vector. Oh no, they define it like that. Nice. Okay. It's the unique vector such that if you pick this point, then this is at right angles to V. So what we have is that note the vector that goes from so W will either be the projection of V onto W plus a bit, and this bit will be orthogonal to V. So this leftover bit is orthogonal to V, and it is called the component of W orthogonal to V. I say this now because what will happen sometimes is that they'll use statements like find the orthogonal projection of W onto V, find the orthogonal component to V of W. And what will happen is that people will see orthogonal and they'll go straight to finding the orthogonal projection. But if they're saying the orthogonal component is actually perpendicular to V and the orthogonal projection is actually in V. Okay, that's the basic idea off the top of my head. So what we can do is we've written it as if it was the name of a function. See, we've got PRV function of W. It's actually written as a function that's acting upon the vector W and producing an answer, and that's the way we're thinking of it. PRV is a function that sends R whatever to R whatever. So in this case here, it takes 2D vectors in and it spits out as answers other 2D vectors. And when we say vector, we mean point, because that's how mathematicians think about vectors most of the time, unless they're adding them together. Okay? So the most common ones you'll see are like R2, e.g. this one goes from R2 to R2. And when we think about it as a function, this function is a linear transformation. It has the property that if I figure out the projection of two different vectors and add them together, add the two answers together, it's the same answer as if I figured out added the vectors together first and then did the projection. And if I multiply this vector by 2, then I'll multiply the answer by 2 as well. So it's a linear transformation, and being a linear transformation, it must be possible to write it as using a matrix. So I'm getting a bit ahead of myself though. So it turns out that if you want to do an orthogonal projection in R whatever onto a subspace of V which is whatever, the way to do it is, we drew some pictures, but if we're in R7 we can't draw pictures. The way to do it is to first find an orthonormal basis for your subspace. So here's how we're going to have to do it. We have to find an orthonormal basis for V, and I shall call them V1 up to V R. Okay, so it's very important that it's an orthonormal basis or this process won't work. If it's an ordinary basis, it won't work. If it's just an orthogonal basis, it won't work. It has to be an orthonormal basis. And what that means is the length of all of them is 1, and when you dot two different ones together, you get 0. Okay. So you have to first find an orthonormal basis for V. Okay. If you've already got an orthonormal basis in your head or given to you, then that's great. And then the projection onto V of W is... All right, well, here's the thing. I'm going to write it this way because this is how I always think of it and it allows me to get it right. The projection onto V of W is going to be a vector that is in V, because the whole point of this is to find a vector that is in V that is as close as possible to W. So I want a vector that's in V, and since this is a basis for V, everything in V is a combination of those things. So it's got to be something times V1 plus something times V2 plus something times V3 all the way up to something times VR. It has to be something like that because everything in V can be written that way. And the magic of an orthonormal basis is that the correct coefficients are done with dot products. And that's how to do an orthogonal projection. Right. If we are very lucky, we're not lucky. If we think carefully, we know that we can find an alternative way to do this. Because it's a linear transformation, it must be possible to be done with a matrix. Yep? It will indeed. Yes. So if you do not already have an orthonormal basis, then you might need to do the Gram-Schmidt process to get there. If it's already an orthonormal basis, then of course you don't have to do anything. Like if in the exam question they said, this is an orthonormal basis for V, then you wouldn't do the Gram-Schmidt process because it's already been done. So, okay. But this is sort of, you have to do it, it's sort of like step 0 really. You have to have that before you can even start doing this process. And that's how to do an orthogonal projection. And the thing is, this is a function still. I keep changing what the W is and I could get the answer for all these different W's and it's a function. And so it takes vectors in, it spits vectors out. It should be possible, because it's a linear transformation, to rewrite that using a matrix. But first let me do an example of actually finding one. Okay, find the orthogonal projection of, I don't know, 135 onto V, which is the span of 0, 1, 1 and minus 2, 0, 3. Okay, that's going to be my example. Okay, so I have all the pieces I need. I have a vector space, I have a subspace that I'm projecting onto. It's this subspace here. And I have a vector that I want to project onto it, and it's this vector here. So I'm finding PR sub V of 135. I don't know where the 9 came from. Okay, so step 1 is I have to find an orthonormal basis for V. And it's perfectly okay to use ON as your abbreviation for orthonormal. So first I'll just check that they're not an orthonormal basis already. 0, 1, 1 dot minus 2, 0, 3, I'll get 0, 0, the dot product is 3, so they're not orthogonal, so it's not an orthonormal basis already. Okay, so I have to do the Gram-Schmidt process. Okay, so the Gram-Schmidt process goes normalize first. So I get to pick which vector is the first vector, so that one looks like it's going to be hard to find the length, so I'll do this one. So the length of 0, 1, 1 is the square root of 0 squared plus 1 squared plus 1 squared, which is root 2. And so therefore my first vector is going to be that. Divide the vector I first chose by its length. Okay, so this is very interesting what I'm about to say. Orthogonal projection uses, the Gram-Schmidt process technically uses orthogonal projection to do it, which seems like circular reasoning if we use orthogonal projection in order to figure out how to do orthogonal projection, but it's more like a mathematical induction thing. We can figure out how to do projection on a line, and then using projection on a line we can figure out how to do projection in a plane, and using projection in a plane we can figure out how to do projection in a 3-space, and so on. So in my head the Gram-Schmidt process goes normalize, project, subtract, normalize, project, subtract, normalize, project, subtract, normalize until you're done. So that's what I'm going to do. So I'm going to do the projection of my second vector onto my first vector. It may be easier for me to call these u1 and u2. Okay. So let's see. u2 dot v1 which is the 1 on root 2 is still there. 0, 0, 3. Okay. And so the projection will be this. Which is 3 on 2, which is 0, 3 on 2, 3 on 2. Okay, so I'm going to do the thing I would normally do to do a projection. I'm going to do the dot product. I'm going to do the dot product times the vector, and that's what I get. And then I'm going to subtract u2 minus this projection. What was u2? Minus 2, 0, 3. So what have we got? Minus 2 minus 0 is minus 2. 0 minus 3 on 2 is minus 3 on 2. 3 minus 3 on 2 would be 3 on 2. And that's what I've got. And then I'm going to have to normalize. So before I normalize, it would be useful, I don't really need this vector that I've just got, I just need the direction that that vector points in. So it would be useful to multiply that by something so that it doesn't have any fractions in it. And so I'm going to call my v2 dashed minus 4, minus 3, 3. And in fact, I might just make it so there's only one minus in that. Okay. So the length of that is square root of 16 plus 9 plus 9, which is awful. 16 plus 10 plus 10 would be 46, so 44. Okay. Here we go. Okay. And so therefore my real V2 is 1 on root 4. Yeah, totally would be 34. Well done. I'm glad you're feeling brave enough to tell me when I'm wrong. That's important. So that's my other vector. So now I have an orthonormal basis. I guess a basis technically is a set. Okay. It looks awful, but there we have it. And so therefore, so step 2 is to actually do the projection. The projection onto V of the vector I first thought of, which was 1, 3, 5. will be the various dot products, right? I'm not going to actually do an equal sign yet. I'm just going to do some calculations. 135 times 1 on root 2, 0, 1, 1. Dot product. So 0 plus 3 plus 5 is 8. And 135 dot 1 on root 34 times 4, 3 minus 3 is 4. Plus 9 is 13, minus 15 is minus 2. I just want to check that. 4 plus 9 is 13, minus 15. 13 minus 15 is minus 2. Yep. So those are the coefficients I need. So I know that the projection of V onto 1... I should really have done this as a heading, like, you know, find the projection. That would have made more sense. Yeah, okay. The projection of 135 onto V will be this number times the matching vector plus this number times the matching vector. And so, get 8 on 2 times 0, 1, 1, minus 2 on 34 times 4, 3 minus 3. It's just awful. 0, 4, 4 minus 4 seventeenths, 3 seventeenths, minus 3 seventeenths. 17 times 2 is 34, isn't it? Yeah, okay. It's 20 plus 14, yep. And so that would be whatever it is. I know the first coordinate is minus 4 seventeenths. 4 would be another 17, so 44 plus 51. Oh, no. 3 times 17 is 51, so 68. 68. Which makes sense, because 2 times 17 was 34, so it'd be another 2 times that. Of course, 68, okay. So 68 minus 3 would be 65 on 17, and 68 plus 3 would be 71 on 17. And that's my projection. Sweet. There you go. This is the nearest point on that, and it's a plane because it's got 2 vectors as its basis. This is the nearest point on that plane to the point 135. So it's not that far from the 3 and the 5, because it was 4 minus a bit, which is near the 3, and 4 plus a bit, which is near the 5. But this is quite far from the 1, and I don't know what that means. It means the plane is sort of pretty far away from that thing. That's the orthogonal projection, and that's how to do it. So here's a question. What if I wanted to do this orthogonal projection on multiple different points? Not on 135, but on x, y, z. Okay, and I wanted a formula for what the answer was going to turn out to be if I used x, y, z. That's the question that we're going to answer. And you could imagine trying to do this whole thing with x, y, z in this position here instead of 135. And so we would get like 3x plus 5, 3y plus 5z in this position, and there'd be all these formulas everywhere, and it would be annoying. But we could actually figure out a matrix for this without having to do any of that work, because the standard matrix of any linear transformation has as its columns what you get when you do the operation on the standard basis. So if I wanted to find the standard matrix for this, all I would need to do is figure out what the projection is of the 3 standard basis vectors, and that will be the columns of my matrix. Once I had figured out those, they will be the columns of my matrix. So my basis vectors were these 2 things here. So I'm going to need to do, I'm going to do it all in one go if you don't mind. And of course I haven't left myself enough space. So that's what the projection is. Dot product times matching vector, dot product times matching vector, and add them together. And so 1, 0, 0 dot with this is 0. Well, 1 times 0, 0 times 0, 2, so this bit's gone. And 1, 0, 0 dot with this is just 4. So that would be 4 on 34 times this. So 8 on 17, 6 on 17, minus 3 on 17. And that's the first column of the standard matrix. PRV of 0, 1, 0 will be whatever it is, and that'll be the second column. I'm not going to do it, because I want to do another example before I move on. I'm using stupid symbols. So the standard matrix will be 8 on 17, 6 on 17, minus 3 on 17. Like that. You'll just take those 3 vectors that you've figured out and you put them in as columns. And what that means is that now that I've figured this out, in order to do the orthogonal projection on any vector, all I need to do is put that vector as a column here and multiply the matrix, and it will give me the correct answer. That's how it's done. I feel the need to color code these. Because my symbols aren't the best drawn. There we go. No row reduction, that's the standard matrix. So if now, let's just call this the matrix A. So now, the projection of V onto V of 1, 3, 5 would instead have been calculated by doing the matrix A times 1, 3, 5 as a column. And that would come out as a column vector version of the answer I was looking for. Yep. And so this would have actually come out to, it should have come out to that if it was working. The reason this works is because if it really was a matrix that was doing this, and I wanted to figure out what happened when I did 1, 0, 0, I would put 1, 0, 0 in this position next to the matrix. And when you multiply a matrix by 1, 0, 0, you get 1 and 0 of this and 0, 0 of this, 1 of this and 0 of this and 0 of this, and 1 of this and 0 of this and 0 of this. And so that would tell you what the first column is. So if it really is a matrix, then multiplying by 1, 0, 0 will give you the first column. And so therefore, if it really is a matrix, figuring out what happens to 1, 0, 0 will tell you the first column, and the same for the other columns. So I'm going to do the classic example that everyone always asks me about. find the standard matrix of the orthogonal projection onto the line y equals 5x in R2. Okay, so we're seeing orthogonal projection as not of any particular vector, but of all the vectors simultaneously. And an orthogonal projection requires us to have a subspace to project onto, and this is the subspace we're projecting onto. That's the subspace I want. And we're going to need to find a standard matrix for that. And I know that when I do a standard matrix, all I need to do is figure out what happens to the standard basis. So in order to find this standard matrix, so let V the subspace with equation y equals 5x, what we do is that we need the projection onto V of 1, 0 and the projection onto V, I always put the V in the wrong spot, the projection onto V of 0, 1. Once we have those two answers, they will be the columns of the standard matrix. So, if I'm going to do an orthogonal projection, I need an orthonormal basis for my subspace. So at the moment, I don't even have a basis ordinary for my subspace. My subspace currently has an equation, so I'm going to first need to find a basis for V so that I can find an orthonormal basis for V. So, okay, so V is made of all the vectors that have y equals 5x, and so if the y is 5x, I can replace the y with 5x, which is x times 1, 5, and so 1, 5 is a basis. If this had been in 3D, I would need to have dealt with a 2D function, and I would have had to get my basis a little differently to that, possibly solving the single equation that I had. But in one dimension, I can just sub in the y instead of 5x, and that gives me all the multiples of 1, 5. Doing all right? Cool. So this is a description of all the points in V, and so therefore 1, 5. So I need an orthonormal basis for V. I've only got one vector, and I'm going to have to do the Gram-Schmidt process. So Gram-Schmidt process begins normalized for the first vector, and that's the only vector I have. So the length of 1, 5 is the square root of 1 squared plus 5 squared, which is root 26. And so therefore, an orthonormal basis for B is 1 on root 26 times 1, 5. Okay? So I finally have an orthonormal basis for V. Now that I have an orthonormal basis, I can do the projection. And so therefore I know that the projection onto V of any vector is vector dot 1 on root 26, 1, 5 times 1 on root 26, 1, 5, and there's no more to it because there's only one vector. I didn't need to technically write this step down, but that's how the orthogonal projection is going to go. And so I need the projection onto V of 1, 0. Okay, so 1 times 1 is 1, and 0 times 5 is 0, so I get 1 times 1 on root 26. And so that would be 1 on 26. Okay, so that's column 1 of the matrix that I want. And I need to do the projection onto V of the other basis vector. Oh, it's not 1, 0, it's 0, 1. Okay, so 0 times 1 is 0, 5 times 1 is 5, so I get 5 on root 26 times 1 on root 26, 1, 5. And so what have we got? We've got 5 on 26 and 5 times 25 on 26. And that's the second column of my matrix. And so therefore, the standard matrix is 1 on 26, 5 on 26. That's this vector as the first column. And 5 on 26, 25 on 26, which is this vector as a column. Ta-da! Yes?
Can you swap the columns?
Sorry?
Can you swap the columns?
No, you cannot swap the columns. So 1, 0 has to go in the first column, and the result of 0, 1 has to go in the second column. Let's just check if this is working. If this really is the standard matrix for an orthogonal projection onto this subspace, if I pick a vector that is in that subspace, nothing will happen when I multiply it by this matrix. Just to check. The projection onto V of the vector 1, 5 is 1, 5, right? Because it's already in the subspace, so when I do the projection, nothing happens. So it should be this should come out to 1, 5 if we've done it right. So let's just see what happens. So we get 1 on 26 plus 5 times 5 on 26. Okay, and this we get 5 on 26 plus 5 times 25 on 26. So what have we got? 1 on 26 plus 25 on 26 is 26 on 26. That's good. 5 plus 100, so 130 on 26. So that's totally 1. And 130, well, that'd be 10 times 13, and the bottom's 2 times 13. And so we get 5. Sweet. It should, that's working. So that's not a very good trick. I mean, that doesn't necessarily check that it works for every vector everywhere, but it certainly checks that it works for vectors that are on the subspace. So it's just a useful check to see if you've done your fraction arithmetic right earlier. Yeah. All right. Okay. Orthogonal projection. I'm just organizing my notes. This goes here. This goes here. This goes here. Okay. All right. Which means I have about 20 minutes to do one more thing. So what am I going to do? The eigenthings is probably going a bit more than 20 minutes.
What about the, you have a number, like 0.609 and
Yes.
that thing?
You asked me that last week. I can talk about that. So maybe I'll do a few random series things. So I will keep answering questions about rate power series and stuff, infinite series, for the rest of this. If you've got anything to ask. Cool. You should know that there's a couple of written seminars on eigen things on the website already, so check them out. I've tried very hard to... they're under the old curriculum, but it's pretty much the same. So check them out if you want to watch what I have to say. You can always come to the Maths Learning Centre as well. So... let me do some series examples, hey? So my first example will be the one that I was asked just then. Use geometric series to write, I don't know, as a fraction. So I have 3.01924, 924, 924. So that's my example. So it is possible to write this as a fraction without using series. Okay? There are methods that you can look up online or that I can show you that use this that can write a repeating decimal as a series, as a fraction without using geometric series, but we've been asked specifically to use geometric series to do it, so I'm going to use that. But both of the methods require us to think about this a certain way. Okay, so I'm just going to have a look at this number. So I have this repeating part here, and then I have this separately, this non-repeating part here. That's the beginning before it starts repeating. And so what I'm going to do is I'm going to use scientific notation to help me write this number. And I'm going to focus very carefully on these 924s. So, I'm just going to leave the 3.01 here. And this 924, the 4 is in the 10 to the minus 1, 2, 3, 4, 10 to the minus 5 position. So this position here is the 10 to the minus 5 position. So this is the 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. So I have 924 times 10 to the minus 5. And this one is into the 10 to the minus 8 position. And this one is in the 10 to the minus, well, it's 3 more, right? So 5, 6, 7, 8, 9, 10, 11, minus 11 position. And so on. So I can rewrite my number like this. It's not traditional scientific notation. Scientific notation, you would go like 9.24 times 10 to the minus something, but this is better because I don't really want any decimals. So if I was thinking very carefully, I would even have written this as 301 times 10 to the minus 2. Because I really want whole numbers. Okay. Doing well. So already it's a series. I've got a sum of infinitely many things. So this 301 is different. I'm just going to write that one as a fraction already. And this I'm going to take out a common factor. They've all got a 924 in them, so I'll take that out. And they've all got a 10 to the minus 5 in them. This one's got a 10 to the minus 5. This, if I removed a 10 to the minus 5, would leave me a 10 to the minus 3. Because when you divide by 10 to the minus 5, you'll subtract minus 5, which is the same as adding 5. And this one, when I remove the 5, 11 minus 5 is 6, so I'll get 10 to the minus 6 forever. Doing very well. So I'll just write it as a fraction. So here's the thing. This is a geometric series. I have one more thing to do to make it really obvious that it's a geometric series. That minus 6, well, it's 2 minus 3s. And the next one will be minus 9, which is 3 minus 3s. And so this is really this. This is 10 to the minus 3 to the power of 1. This is 10 to the minus 3 to the power of 2. This is 10 to the minus 3 to the power of 4. This is 10 to the minus 3 to the power of n. And so this is another way of writing that. I could have gone straight from here to here if I wanted.
Should it be a 3 instead of a 4? Because you said it's negative.
Oh, yep, totally 4. Yep. I got carried away because I'd already written a 3 here, and so I wrote the next number. Well done. It happens to me all the time. If I already see the number on the page that I was planning to write, I write the next number after it. It's really bad. It's like doing Hebrew poetry. So now there's a formula for the sum of an infinite geometric series. It's that. 1 over 1 minus this number. Technically it's written with fractions now, so I could probably stop if I didn't have enough time to simplify it, but I should simplify it. Mathematicians and people generally are not comfortable with negative powers inside fractions. And so I would prefer to not have a 10 to the negative 3 in that fraction. So what I'm going to do is I'm going to multiply the top and bottom of that fraction by 10 to the power of 3 to make the 10 to the negative 3 go away. I'm going to be extremely explicit about what I'm about to do, just so you can see what I'm doing. Okay? That's what I'm about to do. You don't have to include that working if you don't feel like it, but I just wanted to make sure it was on the page what I was doing. So I have on the top 10 to the 3, and on the bottom 10 to the 3 minus 1. Because 1 times 10 to the 3 is 10 to the 3. 10 to the minus 3 times 10 to the plus 3 is 10 to the 0, which is 1. Sweet. Nothing up my sleeves. This cancels with most of this to give me a 10 squared. Ten cubed is 1,000. 1,000 minus 1 is 999. So, therefore, if I want this as a single fraction, I'm going to need to times this one by 999 on top and bottom. Which leaves me figuring out what the hell this is. I guess it's 301,000 minus 301. Oh, cool! Yeah! And 924 minus 301 is 623. Awesome. Look at that. I knew I could do it without a calculator. Nice.
Still divide by 3 though.
Yeah, I could divide. It doesn't matter. It's a fraction. So you're right. I could. Yeah, the top one and the bottom one are both multiples of 3, and so I could, if I wanted to, divide them both by 3 if I wanted. But they didn't tell me to write it as a fraction in lowest form. They just asked me to write it as a fraction, so I can stop now that it's a fraction. It's a single fraction now. Okay. So the geometric series bit that was important happened here. So if you're working and you're trying to figure out which steps you can skip writing down, you cannot skip writing down this, and you cannot skip writing down this. Like, you have to write it with the infinite sum in it, or you haven't technically used a geometric series. Your lecturer wants you to write that notation down. So you can do this without using geometric series if you want to at least get an answer. And the classic, I'm just going to So there's an alternative that doesn't use geometric series, and it goes like this. Let x be equal to 3.01924,924, etc. And so what I'm going to do is I'm going to move it up so that the decimal part is only made of repeating bits. So I'll have like 100x is 301.924924, etc. Because another 924 will move up when I do that. And then if I multiply by 1,000, I'll move this all up 1, and I'll still get 924 in that spot. Like that. Nothing up my sleeves. This minus that, the repeating bit will disappear because I've got this thing minus that, and then repeating bit minus repeating bit, and so they'll go away. And so I will get this minus that, which is 99900x. It will be 301,924 minus 301. And so therefore x is 301,623 divided by 99900. Magic. However, it's important to note that this didn't use geometric series, and so it doesn't count as an answer if you've been asked to use geometric series. You may get possibly 1 mark for having the half of the marks for having the correct answer. Yep.
What if you did geometric series and screwed it up, did it this way to get the right answer, and just crossed out your right?
I don't know what they would give you. If it did the difference between passing and failing, they would probably give you the mark. But otherwise, no. So, yeah. Yeah, if it made a difference between a credit and a distinction, they would probably give you the mark if you did that. But they will try their best. They're not technically supposed to mark anything you've crossed out unless they're looking for that extra mark to get you over the line. So, yeah. Cool. But at least this only took like 4 or 5 lines, so it's at least a way of checking that your answer was right for the other one. Yeah. Okay. So something else series-y that you might want to ask about. I know, I've got one. Just a second. There we go. Find the sum of this series. The sum from n equals 13 to infinity of 2 to the n plus 1 over 3 to the power of 2n. This was a classic one that comes up in the assignments that people had trouble with, so I thought I'd do it now. Okay, so there are some clues here that tell you what to do. The only series that you know what the sum is a geometric series, unless it happens to turn out to be one of the Taylor series that you're supposed to remember. Okay, so they're the only options for you to being capable of figuring out what the sum actually is. So for them to say find the sum tells you that it probably is a geometric series. And that is confirmed by the fact that almost everything here is involving powers. And so I can use powers, and geometric series are about powers. So if I can rewrite this in terms of something to the power of n, then I have a chance of using geometric series to find it. So I'm going to work my way through this. So that's 2 to the n times 2 to the 1 on the top. And this would be 3 squared to the n on the bottom. So what I'm doing is I'm separating out the pieces so that I have somewhere in my expression thing to the power of n. I don't want thing to the power of 2n or thing to the power of n plus 1. I want thing to the power of n. So with this one, the addition up in the power becomes multiplication. And so now I have a 2 to the power of n. And this one, powers of powers, multiplication here is the same as powers of powers. Okay. So I have a times 2, and since everything is times 2, I can do even better than what I was about to do, and I can do this. And without that times 2, I have 2 to the n on 3 squared to the n, and powers distribute over division, and so that will be this. So several things happened there. This went here. And these two, because they were both power of n, ended up joined together inside the brackets because that's how powers interact with division. Okay, now it's a geometric series. It is thing to the power of n. And I know what the sum of a geometric series is. It's 1 over 1 minus that, only it's not 1 over 1 minus that if it starts at 13. The formula that I know starts at 0. So I would like this to start at 0 instead of at 13. So I have two ways I could approach that. I could think, well, if it did start at 0, I'd just have to take off what happens when n is 1, when n is 0, and when n is 1, and when n is 2, and when n is 3, and when n is 4, and all the way up to n equals 12. And that would be annoying. Or I can do another clever trick, which is once you've seen it, you can usually replicate. All of those terms, it starts at 2 over 9 to the 13, and then 2 over 9 to the 14, 2 over 9 to the 15. I can divide them all by 2 over 9 to the power of 13. Because they've all got that as part of them. And the other way of dealing with it is this. I want it to start at n equals 0. I want an n equals 0 in this spot. And if n is 0, I'm going to have to add 13 up here so it works out to be the correct power. So this one starts at this one starts at 13 in this position, and then 14, then 15. This one will also start at 13 in that first position because it'll be 0 plus 13. And the next one will be 1 plus 13, which is 14. So together they have the same list of powers. So just in my mind, I'm thinking this one has 2 ninths to the 13, 2 ninths to the 14, 2 ninths to the 15. And this one has 2 ninths to the 0 plus 13, 2 ninths to the 1 plus 13, 2 ninths to the 2 plus 13, and they are the same thing. Ultimately, if you take 13 from these numbers, then it's the same as adding 13 to this number. And infinity minus 13 is still infinity. All right, here we go again. Well, power addition up in the power is multiplication down here. And so now I have 2 times 2 over 9 to the 13 times the sum of n equals 0 to infinity of 2 over 9 to the n. And now that is a 0, and so I can use the sum, the story. And that's how you do an infinite sum starting at 0 of thing to the power of n. You go 1 over 1 minus thing. Now, I'm not going to bother trying to deal with, we don't want to know what 9 to the power of 13, that's horribly huge. But this looks very uncomfortable. I don't like fractions within fractions, so I'm going to multiply the top and bottom of this fraction by 9. And that's good enough. I'm going to stop there. Suppose I could go 18 sevenths if I was really feeling. And that's the answer. Yay! This move from here to here is one of my favourite moves. Going, I'll just multiply this and this by 9. I don't have to figure out what the bottom is by fraction addition and then flip it over. Just have to multiply everything by 9. That just makes me feel happy. Yeah. All right. It's one of my favourite fraction algebra arithmetic moves. Well, they're the two major examples that everyone asked me about when we were doing series in the Maths Learning Centre, so it's a good thing to say now. Anything else burning in people's minds?
All these series and stuff like power series, P series, what's the main ones to really have ingrained in your head?
The main things to remember. Okay. What I might do is go to the Maths 1B page. And there is a little handout here about tests for convergence. And importantly, the first thing on the list is the series that you know. So if you wanted to test if a series converges, then the first thing is to check if it's on the list of things that you know already. The second thing is to do what I call the divergence test, but your lecturer probably called the vanishing criterion. And then alternating series test and then the ratio test are things to try. Or at least in your head you go, do you think these will work? And these are the classic series. The harmonic series, which is 1 over n. The alternating harmonic series, which has minus 1 to the n over n. It doesn't really matter if it's minus 1 to the n or minus 1 to the n plus 1. No one really cares. The p series, which is 1 over n to the p. So note that the p is constant, it's always the same. So it'll be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, or 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, etc. It doesn't really matter what that p, the p stays the same, but the number that is inside it changes. So that one converges depending on whether the power is more or less than 1. The geometric series is the classic, and in that one it's the power that changes when n changes and the base that stays the same. And then the other classic is the Maclaurin series for e to the x, Taylor series with x at centre 0, which is one that they expect you to recognise as well. So if you see any of those, you can go converges or diverges, depending on which one you see. And they're the ones they want you to remember. Yep?
Did you say to memorize the Taylor series with cos and sine?
Your lecture notes, the printed lecture notes, that they give you, say that you are supposed to memorise the Taylor series for cos and sine. So yes, technically they should be on this list as well. I did give suggestions in yesterday's seminar about how to memorise them. As long as you can remember the one for e to the x, you can just change the n to a 2n plus 1 for sine and to a 2n for cos and whack a minus 1 to the n in the front and it should work. So they're the classics, and then there are a few tests that you're supposed to know how to do. All right, that's what I would say is the things that you need that are on this handout. So I'll put a link to this handout. It's already on there, but I'll put it with this revision seminar as well when I put it on the website. So you can go and find it. Yeah. So I like organising it this way. And you'll notice that, the first column is the names, what it's called. The second column is what the formula looks like. The third column tells you when it converges and when it diverges. And the fourth column tells you what the answer is. And the only ones that we know what the answer is are the ones that are on the list of common Taylor series. Yeah. So I've tried to organise it to really ram that point home. Yeah. So importantly, when you are doing a radius of an interval of convergence, at the two endpoints, there's several seminars on interval of convergence, so you can go look them up. But at the two endpoints, you're not going to be able to use any of your classic tests at least not the ratio test, to tell whether it converges. And what you're going to have to do is look at it and go, is it on my list of things that I know? I should also point out that the harmonic series like 1 over n, if it's 1 over 2n plus 1, it will still diverge. As long as it's linear on the bottom, it still diverges. So I could have, instead of n, I could have 3n plus 1 or 5n minus 7. As long as it was a linear thing in n on the bottom there, it will still diverge. That's just, I don't know if the lecturer sort of used that fact at least once in the lectures and they spoke it out, but I don't know if they expect you to remember that, but I'm just saying it now. Yeah. Okay, and that goes for any of these powers actually. I'm just going to write that down while I'm thinking of it. Okay, see the handout, but also note that will also diverge, and it doesn't matter what it is, any linear function down here will also diverge. And the reasoning behind that is that it's between two copies of the harmonic series. So you can actually prove it. So you can say that if you just go up to a specific n, and rather than go to infinity, so just a second. So this thing is 3n plus 7, and so something plus 7 is a little bit bigger than just 3n, and so since the denominator is bigger, the fraction is smaller. So this is a little bit less than 1 over 3n. Okay? No matter what n is, 1 over 3n plus 7 is less than 1 over 3n because 3n plus 7 is a bit bigger, and so therefore the fraction's smaller. But it's also as long as n is more than 7, 4n is more than 3n plus 7. So if n was 7 or 8 or 9 or 15, well then the 7's less than n. And so actually it might be easier to do this a different way around. Let me just write that again. 3n plus 7 is definitely more than 3n. And it's definitely less than 4n if n is greater than 7. And so when you flip them upside down, you get this. And so when you do the sum up to point n, what you get is this. This one will work as long as n is big, the capital N is big enough. And this is a quarter of the harmonic series, and this is a third of the harmonic series. And so this thing is between two harmonic series, and the harmonic series diverges. So because it's between two things that both diverge, it has to diverge as well. That's it. Yeah, that's the reasoning behind it. I don't think you have to reproduce that in an exam, but I just wanted to point out that there was reasoning that explains why that works. It's about the same as the harmonic series, and that works as well if I had 1 over n squared plus n plus 3, because the biggest power you see is an n squared. When you go back and look at the list of power series, the p series, if it was an n squared, it would converge. So anything that's quadratic will converge on the bottom. So that's sort of basically the idea. So too many letters. Since for large n, n squared plus 3n minus 7 is approximately n squared. And if it was n squared, it would converge because it's a p series. Something like that. So, that's what I wrote. So if it has something like this, that would converge, since for large n, this is approximately n squared, and that converges. And that reasoning sounds pretty dodgy, but there are ways to make it more specific, so that's good enough. So if you happen to see something that's quadratic on the bottom, you can just say it converges. And the lecturer did that at least a couple of times in the examples, so you're allowed to do it too. Yeah. Okay, I think that'll do. I have done quite enough revision seminars this semester. Thanks for coming along for the ride. Maths Learning Centre is still open this afternoon and on Thursday and Friday. And, well, it is open on Monday as well, but that will be too late. But we are open all the way up to and including O week, and in O week we start to be open 10 a.m. to 4 p.m. So if for whatever reason you have a replacement exam, we're still there to talk to if you need to. All right. I'll see you around. Bye.